Good morning, everybody. Welcome to our lecture on image analysis, image processing and analysis, and so on and so forth. Here's what we're going to do today. Largely, we will be talking about rather silly things. Really nothing big there. Towards the end of our lecture today, we will begin to talk about mesh warping, which is much more interesting than everything we are going to do up until here. But we also have to discuss the results of the survey. Right? A couple of weeks ago you took the student survey. The results are in and I am obliged to discuss them with you. So it's actually a good thing to, don't take too long today for the lecture. So today is the ideal point in time to do these funny, silly things. But let's begin with reminding ourselves what it was that we discussed last time. Last time we began in earnest, right? Not just in terms of looking at funny examples, but actually looking at certain warps in terms of how they can be computed. So we began in earnest to study the idea of image warping. Among the different effects we discussed was, for instance, this fisheye or lens effect, where we can think of an image like this resulting, let's say, sort of physical metaphor, resulting from an image like this, if we were to put a magnifying glass over some parts of the image, and the question is, what kind of mathematics would we have to apply to the coordinates of the pixels to simulate this physical metaphor in our computers, right? It's called fisheye or lens effect just because we can think of this image resulting from this image by superimposing magnifying glass or a lens over certain parts of the image. We discussed the basic idea in terms of what we would have to do to a one-dimensional function. Images are two-dimensional functions defined over two coordinates. We began studying this with respect to one-dimensional functions defined over just one coordinate. And we said that now this magnification basically means that we have to apply a transformation to the coordinates of the function we are given, such that this transformation causes small coordinate values to become even smaller, whereas it does nothing to large coordinate values. So large coordinate values are supposed to remain untouched by this transformation, and small coordinate values are supposed to be mapped to something even smaller. And well, if we continue formalizing this idea in terms of mathematical operations, we can think of this in two ways. Either we think of it as a problem of addition or a problem of multiplication. If we understand this transformation as something additive, then that would be to say that we have to add something negative to the given coordinate if that coordinate value is small, because if we add something negative to a small number, it becomes even smaller. And if that coordinate is rather large, then what we have to add is 0. With respect to multiplication, we can formalize that as we have to multiply something to the coordinate that is less than 1 if that value of x is small, or something that equals 1 if x is rather large. And if you accept that, then you are free to choose whatever functions you want in order to create these effects, as long as they have this property, function t, the warp function, has this property that it basically leaves large values untouched, or does nothing to large values, becomes the identity function for large values, but sort of makes smaller values even smaller. As long as you can accept that, then of course there are infinitely many possible functions out there. And in these examples, I am showing you two possible choices. The x is called r now. R is for any pixel the distance. So say I have superimposed the magnifying glass over this pixel. This is the center of the magnifying glass. And then every pixel in this image has a certain distance, as a radius, with respect to this center of the magnifying glass. And that radius is called r. And that r has now the function of the, or assumes the role of this x here. So these are functions with respect to r, and you see you can choose them basically to your liking. Here are 2 lenses, and here are 3 more lenses. I don't know, it really, there is no science here. This is just playing around. This is just playing around with mathematics to create funny effects with images. That was what we discussed about fisheye warps, and I emphatically pointed out that if you read about these things on the internet or in certain textbooks, they suggest to compute these warps by iterating over the pixels of the destination image and transforming the coordinates of those pixels into polar coordinates, and then do these warps with respect to r, which is one of the 2 polar coordinates. Do these warps with respect to r, and I said, well, we can do much better. We can do this in terms of vectors, and of course this radius, the absolute value of this radius, can also be thought of as the norm of a certain vector, this radial vector here. If mu indicates the center of the magnifying glass and x indicates the coordinates of the pixel we are about to warp, then we can define this vector r. It of course depends on x. Mu is a constant and shouldn't change when you compute these effects, but of course this r is basically a function of the current pixel coordinate. Now if we do it like that, we can think about this warp function as a function of 2 parameters. And the first one is of course the location of the magnifying glass, and the second parameter is, well, the pixel coordinate of the pixel we want to warp. And we can think of this as a vector addition. This capital delta here is again a vector. This is a vector valued function whose argument is a vector. Right? This mu minus x is a vector, and delta is a function that produces a vector. This is why I have typeset in boldface here. So basically all of this in red is a vector, and we basically add a vector to this coordinate vector x. Of course, this vector has to be 0 if the distance of x to mu, the center of the magnifying glass, is large, and it has to have a certain norm or magnitude, and has to point in, which is that anyway, has to point into the direction of the center of the magnifying glass if the current coordinate is rather close to the magnifying glass. So note that on this slide I have written the warp function in terms of a vector equation, and I have highlighted a certain part of that vector equation in red. And here is another example. Actually this illustrates the function t of x. Here you see I have written it in form of a vector equation, and this factor in front of this radial vector here basically is a number that is very small if x is far away from you. If this is very small, then all of this becomes 0, nothing changes, x remains untouched. And this scaling factor in front of the vector here is not so small if this x is not so far away from you. So this indeed realizes this warp. And what I did here, obviously I placed the magnifying glass at row coordinate 200 and column coordinate 150, so that's about here. And this parameter sigma, that sort of gives us an extension of this magnifying glass, was set to 150. There you have it. This is the image you get if you apply to compute this new function from the old one. We also talked about the idea of computing these wave effects. Physically, the metaphor we can think of is that the image we are given is painted on the bottom of a swimming pool, and then we throw a stone into the water, and that stone, when it hits the water, will cause ripples and waves, and those waves, if we look down to the bottom of the swimming pool, will distort the image we see. So this is the physical metaphor, probably, if you need one. The question is, so then it would look like this, right? Depending on the weight of the stone, it might be a very high frequency wave or a rather low frequency wave. That we don't have to discuss the merits of this physical metaphor. The question is, how can we do that? Again, we looked into that, first of all, from the point of view of a one-dimensional warp function, wave function applied to a one-dimensional function. We found that it's probably a good idea to consider warps like this. So the transformation of the coordinate would be given by x plus some alpha amplitude times the sine of some nu frequency times x minus phi phase. We are all familiar with these parameters by now, and I'm stressing again that even though if you look it up on the internet or in textbooks, you will find that people suggest to go to polar coordinates in order to compute r and phi value, because now we have two phi's anyway, to compute radial values for every pixel and then compute the warp with respect to this radius parameter. I say we shouldn't do that. We can do this in terms of vectors again. Can again consider this vector r, which is exactly defined as before. It is mu minus x, where mu is the center of this effect. That is the location where the metaphorical stone would hit the water. We call that point mu. X is the coordinate vector of the current pixel, the pixel we are about to warp. And we can again rephrase this warp function in terms of vectors, depending on two parameters, r being the vector pointing to the center of the distortion, and x is the location of the pixel we want to modify. And again, if we write this in a bit more of an abstract way, we can express it as x plus some vector valued function delta. And again, note that I am emphasizing this here. And last, but certainly not least, we discussed the idea of computing these swirl effects. Here, a metaphor could be that, I don't know, you have an immersion blender, and you put it in here, and it turns the image locally, well, depending on some parameters, rather quickly or not as quick. And the radius of this distortion might be rather small or rather large. Again, this depends on your liking. We'll even have to discuss this here. We try to understand the basic idea behind this effect, and whereas the two effects we have discussed so far, basically warps of this parameter r, now we look into warps of this parameter phi. Basically, we have to find a function, if we want to, that, well, given the parameter r and phi of a certain pixel, x with respect to a certain center mu, does something to the angle phi, produces a new angle phi prime. And it's our job to define functions that would do this. Here is one such function. And once again, note that we can do this in terms of a vector equation. Right? I have emphasized this once more, and again, you can choose whatever you want here. As long as it warps the angle, it will create a swirl effect. And here is the kicker. Why am I so eager to point out that all of this can be done without having to explicitly transit to polar coordinates first, but to do it in terms of vectors? Because this immediately allows us to generalize all the effects we have seen so far to cases where there are multiple centers of distortion. And this is why I emphasize that we may think about these effects in terms of central forces, like as a physicist would do, because once we think like physicists, we can immediately make use of this principle of superposition. And that is to say, we could compute warps for a single image where we are given not just one, but say n different lenses or different locations where a stone would hit the water, or different locations where we would insert an immersion blender. So we could compute these effects with respect to different center points in one pass, right? Just by adding all these vectors together. Of course, you can also do this if you transit to polar coordinates, but then it is really much more of a hassle. And this is how smart people would do it. Interestingly enough, if you read it up on the internet or in certain textbooks, they never discuss this case. And that should make you wonder why. Yeah, well, so I have, this is really just an equation that indicates the general principle. If there are different centers, n of those, that would indicate the center of these effects. We can compute the radial vectors for each of these centers with respect to the current coordinate x, of course. And then, depending on what we want to do, we need more parameters. But these are basically, for instance, those alphas, nus, and phis here. Depending on the effect, you need more parameters. And I'm ever so generally indicating those parameters by some numbers pi. I really don't care about what effect we are talking right now. I'm just saying you can compute these warps with respect to several centers simultaneously, and of course the warps depend on warp-specific parameters. This is all this equation shows you, and here is an example. How many centers did I use here? What would you say? 3, right. Obviously there was one here, one about here, and one there. And I really computed this image in just one pass. Yeah, here we don't really see that. That is an artifact of the wave effect, because it comes so visually distorted that we don't see that there are actually several waves. But again, one wave starts here, one starts somewhere here, and one starts there. In the next example, it is more visual again. So obviously one immersion blender is here, turning this way. One is here, turning that way. You see, depending on how you choose the parameters, you can do whatever you want. And the last one is here. All of these images were computed in one pass. And in all of these images, I considered 3 centers for those effects, and the coordinates of those centers were all the same. Yep, there you have it. This is why I so emphatically point out that all of this can be done in terms of vector transformations, because if you do it in terms of vector transformations, you can do more complicated things in a rather easy fashion just by adding all these distortion vectors together. Okay, Now, on to the silly stuff. What we're going to discuss in the next 30 minutes or so is really silly. Right? But it is good to see how these things are done. For instance, the pixelize effect has a certain importance in, I don't know, if you have to, say you were working as a reporter as a newspaper and there is some image and for some reasons there are certain aspects of the image you have to safeguard the identity of a certain person, so you sort of have to distort the image such that the person is not to be recognized anymore, or you have to block out certain parts that would violate certain ethical standards, whatever. But you want to show the picture anyway, so one way of doing that is to pixelize it. You have all seen that already, I hope, right? Like pixelized images. And we can think of this effect as artificially reducing the resolution of an image. And by that I mean that if this was the original and we would zoom into it, it would become blocky. Right? We saw that at the very beginning of our lecture, because images are digital in nature, that is, they are space, domain and range are discrete. So if you enlarge them large enough, they become blocky. We can do that artificially. What I did here is I took this image and I combined every patch of 10 by 10 pixels into a superpixel. So this is the original, this is the image that would result from turning it into an image of superpixels, each of these superpixels of size 10 by 10. Here is how this would look like if I were to go for 20 by 20 superpixels. And on the right hand side, this is what you see in the newspapers. Right? 40 by 40 superpixels. It's hard to make out any details anymore. Right? So it can be done, no big deal. The idea is, as I said already, to combine several tiles or patches of pixels, several collections of individual pixels into so-called superpixels. And what I have done in these examples is that, say, for the 40 by, let's go to the other, even though they are not so visible here. So here is a superpixel. Can you see the slightly brighter one? Here's a row of rather dark and column of rather dark. Here's a rather bright superpixel. And that pixel is of extensions 10 by 10 real pixels. And it's obviously somewhere around this tip of the nose of Asterix. And the value, the intensity value of this superpixel is the mean value of the 100 pixels in this tiny square here. So this is what I have done with these images. This is of course not a law of nature. You can set the values to those superpixels to whatever you want. Maybe the largest value in a certain tile, or the smallest intensity value in a certain tile, or as I did it to the mean. Who cares? The important thing is that this idea of pixelization depends on two parameters, and I call them the tile size X and tile size Y. And basically, those two parameters indicate the size in X and Y direction of those superpixels. I've chosen them for the examples we saw to be of equal size, but that, of course, in general does not have to be this way. Here is how you could do that in Python. And I am pointing out that this is a naive Python implementation. What this does is it sets a certain row value y to 0, and then it has a loop over these row values. And there is an inner loop where we set a certain column value x to 0, and there is a loop over all these column values. And then for the current y and x coordinate in the image, there are yet another two for loops. Again, one over rows and one over columns. Basically, these two for loops are just of the size of the tiles, right? And then we initialize a certain mean value to 0, update it for every local y and x value to the value of the image we are given at coordinate y and x plus y2 and x2. This is basically we compute the mean value over a certain patch, divided by the tile size, and then set these values in the new image. And then we increase this column variable by the size of the tile, so we go over the image like this, and then we do this with respect to the rows. Why is this naive? Why do I call it a naive Python implementation?
Because we have two very similar loops.
Yeah.
Double loops.
Yeah. And actually we have these dreaded for loops here. This is a sort of word-to-word translation from a C program to Python. In C or C++ or any compiled language, you would do it like this. And this is computationally no problem. This is ridiculously fast. There's no mathematics going on here. No complicated functions have to be, no exponentials, no square roots, no nothing. This is, just additions and multiplication. But this is how you would do it in C. And actually I did that in C, but in the lecture we, talk about Python, because in C, of course, these couple of lines would require me to write even more lines, slightly more lines, right? But this is a direct translation from a C program to Python. Could you think of a smarter way of doing this in Python, in particular using NumPy? Well, you don't have to, but if you could, that would be great, because then you would have learned something. So if I were to do this the smart way in Python, I would create a mesh grid of y and x values that are spaced like tile size wise. So sort of a coarser mesh grid. Right? And well, then I would not have to have these two while loops here, because we could then do it in terms of mesh grids. And I wouldn't also use these two for loops to compute, this one computes the average color for a certain tile. Wouldn't do that. We already talked about ways of implementing mean filters in O of 1. Could be done here as well. This is just computing local means. And then we could use these methods for slicing arrays to set those values. That's, think of it. If you can think of a way how to turn this into efficient Python code using NumPy, you can rest assured that you have indeed learned something with respect to how to do things in Python. This is naive in Python. I personally wouldn't do it. However, it exposes the basic ideas rather clearly, at least for computer scientists. Right? We can think of modifications of these slicing effects, where instead of computing local means, we can compute local tiles anyway, and we can shift their location in a somewhat random fashion. So again, we have two parameters, tile size x and tile size y, and then I have two parameters, sort of distortion, maximum distortion along x direction, maximum distortion along y direction. And in these two images, the tile size was set to 20 for x and y respectively. Here, these tiny tiles are randomly moved with a maximum distortion or shift value of 10, and there the maximum shift was 20. So you see the difference here. There is, I don't know, more black stuff. Let's look at some more examples. Here we have increased tile sizes, rather small shifts. There are increased tile sizes and rather large shifts. So this is, again, no big deal. In addition to the parameters we discussed already, there are other ones. And here is another naive Python implementation. Probably this is really, the outer part is very much as in the previous code example. And then here, this is extremely inefficient. This is tremendously stupid how this is done, but we randomly compute a value for displacing a tile in the x direction and randomly compute a value for displacing a tile in the y direction. And then I did not initialize this image g-warp. I should have initialized it to all zeros. I just see that now. So this array here should have been initialized to all zeros somewhere up here. But if we have done this, we can simply compute the values in this new image array as it is shown here. Right? We iterate over the coordinates in this new image. And we have to make sure that by adding these distortions to the current pixel coordinates, we do not leave the domain of the image, otherwise that would crash, but we have to make sure that it doesn't. And here you go. Is there a question? No. Yeah, this is, again, very naive. I would not really do it like that, but it shows how it can be accomplished. You know, we can further think of further variations of this. Why square tiles? Why not circle tiles? Turn it into confettis, right? Once we have the confettis, we again could slightly shift them. Do I have code for that? No, I don't. No. Yeah, the only reason why I don't have code for this is because it doesn't fit on one slide anymore. But you know, you could really just think about what you would have to do in this inner loop in order to make it circular instead of square. No big deal. And all of this really is rather silly. It just shows that you can do whatever you want to an image as long as you have enough fantasy to think about crazy ideas. I actually like that. I don't know why you never see those in practice or out there in the world. This is very easy to accomplish. And here is yet another idea. This is something I have seen out in the wild. We can think of computing radial tiles. That is basically to compute these pixelized effects in polar coordinates. And by that I mean, so this is the original image, and then somehow I create something like that. And let's go to the next slide, because this is more pronounced. Here you see the effect. So this is the pixelized effect, but this time applied in radial coordinates. Right? Instead of tiles with respect to x and y, those are tiles with respect to r and phi, and here is how I did that. So we iterate over the image, compute the polar coordinates, and then this is the warp. Sort of, this is this r value. Okay, so there's a certain difference between these images and the ones I've shown you so far. Here, what I've done is that these radial tiles do not show the average value, the mean value of such a radial tile, but every pixel in this radial tile is set to the value that was found here. It was found for the R value where we compute modular division here, modulus. And once we have computed the value R from where this color value or intensity value is supposed to be read, we transit back to Euclidean coordinates and set the value correspondingly. And now, done with that, this is really, it's not necessarily worth any further discussion. This is just to show that by now, well, let me go back. This is just to show that by now you should be so comfortable with the idea of doing something to the coordinates of an image you are given that you basically are able to do whatever you want. If right now you could think of some effect, well, wouldn't it be cool if you should be able to do this? You should be able to, and this was just to show you that there is, you know, this is basically infinitely many things you can do. There is no bound to what you may think. It's just bounded by your fantasy and imagination. If you have certain ideas and want to see what happens if you did this to an image, then go for it. Go for it and see how it will look like. You know how that can be done. Now we switch gears again and well, very, very, very slowly start studying something of yeah, whatever, more scientific importance or more practical importance. We are going to discuss the idea of mesh warping. And to motivate that, I have shown you this example here. This is actually 3 pictures taken from my old office at the Bielefeld University. So I had a very beautiful view over the landscape there. And this chimney is part of the university. And you know that your digital cameras these days come with a function that allows you to compute mosaics like that. So you basically take a picture and then move the camera, take another picture and take another picture. Or you do the other direction, doesn't matter. Your camera, most cameras these days, are able to combine these 3 individual pictures into larger pictures like this. And I was incredibly lazy here because your camera usually would not return you this. It would probably cut the image such that the black stuff isn't there. We know why it is there, right? Obviously I have computed a certain warp. And by computing these warps, we have to deal with the fact that the warp function may move us out of the domain of the original image so that we don't know what value to set there, and I set them to black. Your camera would probably like crop the image such that these effects are not visible anymore, but your camera can do it if you provide it with a sequence of images taken with a certain angular displacement. We are interested in the question how this is being done. This is an application of mesh warping, and here is another application of mesh warping. We will also study the question how to turn something like this into something like that. Both results, this one, which is somehow magically produced out of 3 images, and this one, which was just produced out of a single image, are based on the same ideas. And to begin to understand those ideas, I recall a very trivial fact, something that we actually discussed earlier throughout this lecture, not today, but last week. And it concerns the idea of linear mappings between intervals. So let us assume the line of the real numbers, and we define some a and some b, which defines an interval on the line of real numbers, and we say that a is less than b. So this interval is not empty. There is a lower bound a and an upper bound b. And similarly, we define another interval somewhere else. Can be overlapping, does not have to be, but we have another interval from c to d. C is less than d. This interval is also not empty. And we want to map all the values, all the numbers in the interval a to b to the numbers in the interval c to d. Then here's how we do that. This is what we discussed when we discussed linear interpolation. Remember, there we had to compute an offset value delta, which had to be added to a certain function value. Here we are not talking about function values. Here we are interpolating between intervals. Every value x in the interval AB is mapped to a value x prime in the interval from C to D. And this is basically to say that x prime is to D minus C what x is to B minus A. And of course, the lower bounds of the two intervals are A and C, so we have to incorporate them here. Do you understand this equation? I consider it so elementary that I just show you this. I hope it's okay. If not, I have to go get back to this next time. So this is just, you know, x prime is to B minus A, while x is to D minus C. All right, and now let's generalize this idea to the two-dimensional case. And the simple case we consider in this context is the unit square. So here is 0, 0 coordinate. Then this is the point 1 along the x-axis, and this is the point 1 along the y-axis. And there is a certain point u situated somewhere in this unit square. And of course it has an x-coordinate, which I call u, and a y-coordinate, which I call v. And then we have an arbitrary quadrilateral. And quadrilateral is to say that it has 1, 2, 3, 4 corners or vertices. And this thing is situated somewhere. Well, it could also be over here. It depends on the locations of the vertices of this quadrilateral. For illustration, I have situated somewhere in the first quadrant here. So, but we have 4 corners, x naught naught, x1 naught, x naught 1, and this is basically to indicate the naught naught, the naught 1, and the 1 naught and naught 1. So these 3 indices are chosen arbitrarily. This is, you could have called this one x1, x2, x3, x4, whatever. I use those 2 digits to indicate that this one is supposed to correspond to this corner, this one is supposed to correspond to this corner, this one to that. That's what I'm trying to convey here. Now we've given this quadrilateral situated somewhere, and there is a point x in here, and the problem we want to solve is sort of if these 4 points correspond to these 4 points, then what is the corresponding point x with regard to u? And note that within this quadrilateral, we can think of this point having a certain, well, extension along this line, a certain extension along that line, and along this line or along that line. Is this something we have seen before in this guise, in another context? Is this something that appears entirely new to you, or something where you'd say, oh wait, isn't that just bilinear interpolation? Oh, there you go. Right. When we talked about bilinear interpolation previously, our purpose was to interpolate function values. And now we talk about bilinear interpolation in order to determine coordinates. There's a slight difference there, but in principle, this is something we have seen already. Now, given the unit square and this quadrilateral defined by its 4 vertices, and also given a point u defined by coordinate u and v, how could we determine the corresponding coordinate x inside that quadrilateral? Where would this point map to if this one maps to here, this one maps to there, this one to here, and this one to there? This is a warp of this unit square. Where will this point end up? there's not much to discuss. Basically, this here, x1 naught minus x naught naught, is a vector pointing from here to there. And this point xa along this vector is a scaled version of this vector, so it's, you know, not the whole vector, but something less than the whole vector. The scaling factor is given by the ratio of this size to that size, but that is just u. Right? So it's basically u minus 0 over 1 minus 0, which is u over 1, which is u. So this is just u times this vector would give us this vector, and the starting point is here, so we have to add that. There you go. So we have uncovered this coordinate in this picture. We can do the same for, say, this coordinate. No big deal. And now, as we did in bilinear interpolation, we have two new coordinates, and we can ask for this length here. And again, we have to keep in mind that if we want to obtain this point here, and this has been shifted away from the 0, 0 point, we have to basically add this vector to this point, and we end up here. Right? So this is really straightforward idea of extending these linear mappings to the two-dimensional case. It is something we have seen in the context of bilinear interpolation already. We end up with 3 equations, and we can plug this xa into here and here, or let's say here and here, and this xb into here. Right? We can plug 1 and 2 into 3, and then we get this. And this is the equation now expressed in terms of everything in here is something we know about. We know the coordinates of the 4 corners of this quadrilateral, and we know the value u and v of this point. So the coordinate x that corresponds to u in this warped quadrilateral can be computed from stuff we already know. There's nothing unknown in there. And we can also write this in terms of a matrix vector equation. So I define a certain matrix. Note that here is a 4-dimensional vector consisting of this value u times v, u, v, and 1. And again, like this vector x can be written in terms of its coordinates x and y, say, and we could express it like that, where these coefficients in this matrix are given like so. No big deal. The take-home message is it is extremely simple to map the unit square to any arbitrary quadrilateral. There is really not much going on. If we look at that, I already said it, it warps the unit square to something else. Right? It's a warp function. It is again something that modifies certain coordinates we are given. Given this coordinate u, it produces a coordinate x. This is exactly what we defined as a warp function. And these kind of warps here, with respect to the coordinates, not to the function values, and of course, again, bilinear. This is really in bilinear interpolation. Here we are interpolating coordinates. So this is just another bilinear map. They have certain interesting properties. One of them is, let me go back to the matrix. If we set these two entries of this matrix to 0, which is basically to say that this somewhat strange factor of u times v, this guy here, this is strange, right? It looks, but why is it? But if we set those to 0, then whatever is here doesn't make any contribution to it. Then all of this becomes an affine mapping. And we know that affine mappings are scaling, shearing, rotation, all the stuff we discussed much, much earlier. If A and E are 0, then this is something we have seen already. Another property of this is that horizontal and vertical lines are mapped onto lines. And ratios between equidistant points remain constant. There's nothing going on with respect to ratios. Funnily enough, diagonal lines become curves. Let me see if I have a picture. Here it is. So here we have a horizontal line which is mapped to a line. Here we have a vertical line which is mapped to a line. Let's pick out some other vertical line. This one is mapped to a line. But here we have a diagonal line which is mapped to something curved. And this length, or this length is to this length, or this length to this length. These things are being preserved, but funnily enough, certain lines, not all of them, right? Because this diagonal is also a line, but certain lines, depending on the locations of the vertices of that new quadrilateral, are mapped to something curved. If we first compute a warp from here to there, and then would define yet another quadrilateral, and warp from this one to the third one, that is, if we would compute two consecutive such bilinear warps, the result is not a bilinear warp anymore, but something that is called a biquadratic warp. And unfortunately, if we want to go from, like, first we do the transition from this representation to that one, and then want to go back, can be done, but it's also not a bilinear function. That is to say, the inverse of such a bilinear warp is not bilinear. Let's see. We can see this by looking at one of the two equations. When I say one of the two equations, I mean that we have one equation for x and one equation for y. And here I am looking at the equation for x. Right? We can solve this one for v. No big deal. And we can then plug our newfound knowledge as to how v has to look like into the equation for y, and then do a lot of algebra. All these E, B, D, C, A, F, G are the coefficients in this matrix. We can do a lot of algebra, and because I am always so lazy, I will substitute 3 new variables. Again, all these coefficients on the right hand side, except for x and y, these are the entries of this matrix. And these are, of course, the x and y coordinates. But if we substitute these 3 variables to simplify this here, we get this expression. So we have a times u squared plus b times u plus c. So this is a simple sort of quadratic equation, which we may solve and find that u is given in terms of this expression. But this is actually 2 expressions, right? Because either we can add this square root or subtract it. And that is to say, not only is this certainly not a linear function anymore, it is not even a unique solution. That is, this inverse mapping, if we have computed a bilinear warp from some quadrilateral to another, and now we want to go back, the inverse is surprisingly more difficult than we would naively think. It's not even, there's not even a unique solution. Now, if we want to compute such a bilinear transformation of coordinates, there are these 8 parameters, A, B, C, all the way up to H. In this, once more, I go back to this matrix. Here. So the bilinear warp is defined by these 8 numbers. Everything that is on here in this vector is supposed to be stuff that we know. And these 8 numbers result from, well, looking at these points, these vertices of that quadrilateral. But depending on where they are located, these numbers will be different. So basically the warp is defined either in terms of these 4 points or in terms of these 8 numbers. 4 two-dimensional points, each of them has 2 coordinates, so this is actually 8 numbers on the right, 8 numbers in this picture and 8 numbers in this matrix, so that figures out. So a warp is defined, such a warp is defined by 8 numbers, and in order to determine them, you either have to provide them, right? If you have a certain warp in mind you want to compute, you may provide those 8 parameters, or you may provide the 4 corner points of the quadrilateral you want to map to. Each of these 4 points will have 2 coordinates, so it's 8 numbers. But somehow you have to either provide these numbers or to determine them from data. To determine them automatically, since there are 8 unknowns, will require 8 equations. And I already said it a couple of times, we can determine these 8 equations once you have defined 4 destination points, the 4 corner points of the quadrilateral you want to map to. Each of these 4 points has 2 coordinates, so we are good. Because once you have defined the x and y coordinates of certain points you want to map to, we can easily come up with a system of 8 equations involving these unknowns, and we can then solve for the parameters of the warp. And to wrap it up for today, we now know about several artistic image effects. In addition to fisheye, waves, and swirl, we have seen pixelizing, tiles effects, stuff like that. So you now know how to compute artistic image warps. And in addition to that, we are now prepared, because we have very briefly, very roughly, but it really doesn't matter or merit any further discussion, looked into the idea of bilinear mappings between quadrilaterals. So we are now better positioned to understand how the picture on the right hand side is produced from the picture on the left hand side, and we are also better positioned to understand how the picture in the bottom is produced from the 3 pictures on the top. And this is what we are going to study next time. Because content-wise, this is all I have got for today. Are there any questions? Great. Don't run away, because we have to discuss the survey you took a couple of weeks ago. Thank you.